You know how sometimes you look at a piece of technology and you just think, wow, that's so simple it's actually brilliant? Well, today, we're looking at a device that is the absolute definition of that feeling. It's a little engineering marvel that measures flow with this beautiful precision. And its secret weapon is that it has no secret weapon. No wires, no batteries, no power at all.
Okay, so let's just jump right into the big puzzle here. Imagine you need to know exactly how much water is flowing through a pipe, or maybe how much oxygen is being delivered to a patient. How on earth do you get a precise, real-time measurement without plugging anything in? I know, it sounds like a trick question, but the answer has been a total industry staple for decades.
And the answer is this thing right here, the rotameter. At its heart, it's what's called a variable area flow meter, and it's incredibly popular for a few key reasons. It's simple, it's super cost-effective, and, like we said, it works its magic completely off the grid. It runs on nothing but the laws of physics.
Okay, let's dive into this. To really get how it pulls off this powerless measurement, we've got to look inside. And honestly, its genius is just how simple it is. It's really just made of two essential parts that work together in perfect harmony.
First up, you've got the tapered tube. The best way to think of this is like a racetrack. It's a clear tube that's a little bit narrower at the bottom and gets wider as you go up, and it has these measurement lines marked right on the side. And second, you have the float. This is our runner. It's this small, weighted object that just kind of chills at the bottom of the tube when nothing's flowing. That's literally it, a tube and a float.
So, how do these two super simple components measure something as dynamic as fluid flow? Well, it all comes down to this perfect, elegant balancing act between gravity pulling down and the force of the fluid pushing up. This is where this simple design really shows its genius.
The whole thing works on what's called the variable area principle. The core idea is that the space for the fluid to flow through actually changes depending on how fast it's moving. See, in a normal pipe, the area is fixed, right? But in here, the float's position inside that tapered tube creates this little variable-sized gap for the fluid to squeeze through. And the size of that gap, well, that's the key to the entire measurement. Let's walk through it, step by step. First, the liquid or gas comes rushing in from the bottom and pushes up against that float. This upward force, this drag, starts lifting the float. Now, as the float rises into the wider part of the tube, the space around it gets bigger. This gives the fluid more room to flow, which actually reduces its upward pressure a bit. The float keeps rising until it finds that perfect sweet spot, that point of equilibrium where the upward push of the fluid exactly equals the downward pull of gravity on the float.
So, the whole thing boils down to this beautifully simple relationship. If the flow rate gets stronger, it pushes the float higher to find a new, wider equilibrium point. If the flow slows down, the float just settles lower. So to get your reading, you just look at the scale on the tube, right where the float is hovering. No computer, no sensor, just look and see. So we get how it works, but the big question is why? Why is this classic, kind of low-tech looking design still so incredibly common and trusted in so many high-tech modern industries?
Well, it really comes down to these key features. First and foremost, and we've got to keep saying it, it needs zero external power. That makes it unbelievably reliable, especially in a power outage when other sensors might just die. It also gives you an instant, direct visual reading. There's no screen to glitch out or a complicated interface. What you see is what you get. The scale is nice and linear, so it's super easy to read at a glance. And because the float is just kind of suspended in the flow, it barely obstructs things, which means it creates a very low pressure drop. And that's a big deal because it helps keep the whole system efficient. And this is where it gets really cool, because this brilliantly simple tool shows up in some seriously important places. You'll find them performing these critical functions that affect our daily lives, and you probably never even noticed. For instance, in huge chemical plants, they're monitoring the flow of critical ingredients. Then you can find them at a water treatment facility, making sure just the right amount of chlorine is being added to keep our drinking water safe. In a research lab, they give scientists precise control over gases for their experiments. And maybe most importantly, in hospitals, they are those simple, totally reliable devices on the wall that measure the flow of oxygen being delivered to a patient. Can't get much more critical than that.
So when you boil it all down, the rotameter is just this perfect testament to brilliant engineering. It's a device that simply uses the fundamental forces of gravity and fluid dynamics to give us absolutely critical information. It's proof that sometimes the most robust and effective solution isn't the most complex one. It's the one that achieves that perfect, simple, and elegant balance.
And that leaves us with a final thought to carry with you. The rotameter is such a powerful reminder that elegant physics is all around us.
often hidden in the simplest tools we use every day. So what other everyday objects are out there, quietly doing these complex jobs, powered by nothing more than a brilliant idea?